To try to illustrate the usefulness of conservation of energy and the work energy theorem, we have a few questions that are going to involve simple machines, and then we're talking about systems, how the work energy theorem interacts with systems, and then actually going to talk a little bit about I can use the work energy theorem to think through a motion that is not free fall, so where there is air resistance. All right, so for this first question, piano mover raises a 100-kilogram piano at a constant rate using the frictionless pulley system shown here. With how much force is he pulling on the rope? You can ignore friction and assume, for the sake of argument, that little g is just 10 meters per second squared. So it's easy enough to calculate in your head. So think about what you think the answer is, how big this force is that he's pulling on the rope. And then when you think you have the answer, talk it over to your physics friends, and then unpause the video and let's go over the answer. All right, so it's a 100-kilogram piano, so that's 1,000 Newton piano, but yet piano mover only needs to pull with a force of 500 Newtons. Thinking about this in terms of the work energy theorem, the change in kinetic energy is zero because it's moving at a constant rate. So let's think about how much rope this person has to pull through. If you want to raise the piano up by a meter, he's going to have to actually make the rope shorter by 2 meters because it gets shorter on both sides. So to raise the piano by a meter, he has to pull through 2 meters of rope. And then force times the displacement is the same because the motion is at a constant rate. Then I'm lifting 1,000 Newton piano up a meter. That's a certain work done by gravity. That has to be provided by this person pulling at 500 Newtons through 2 meters. And this is the basic idea behind the simple machine of like a pulley or a block and tackle system. Basically, this bottom pulley, you're getting to have a force of tension up on both sides of the rope. So in a sense, it's sort of a force multiplier. All right, let's try another block and pulley system. So now we have a 50-kilogram person standing on a 25-kilogram platform. He pulls on the rope that is attached to the platform via the frictionless pulley system shown here. If he pulls the platform up at a steady rate, with how much force is he pulling on the rope? So ignore friction and assume G is equal to 10 meters per second squared to make it easy to calculate. All right, so we'll go through and try to calculate what you think the answer is, and then unpause the video and we'll go over it together. All right, so it is a force of only 250 newtons, despite the fact that the weight of the person in the platform is 750 newtons. So let me draw a free body diagram. That's the easiest place to start. So there's my system, and force of gravity straight down, and in magnitude, that's 750 newtons. All right. And there are how many forces of tension pulling up on the system? There's one here, and one here. So 3 times the force of tension. So the vector sum, all 4 of those forces together gives us 0. And 3 times the force of tension equal to the weight means that the force of tension is 1/3 of the weight, so 250 newtons. All right. We're going to talk about systems. Now the work energy theorem interacts with our ideas of what a system is. So a person pulls a box along the ground at constant speed. If we consider the earth in the box as our system, the net force exerted by the person on the system, is it zero or non-zero? So think about what you think it is, talk it over with your physics friend, and then let's go over the answer together when you unpause the video. All right, so the net force exerted by the person on the system is zero. Why is that, or how can you see that? So the person is pulling on the box to the right, and to do that, the person is exerting a force of friction on the ground to the left, and going at a constant speed. This person is moving at a constant speed, so the force from the ground forward on the person is equal and opposite, because of Newton's first law, the force of tension in the rope pulling the person backwards. So those forces being equal and opposite means that the net force they're exerting on the system of earth plus box is zero. All right, let's try another version of this. A person pulls a box along the ground at a constant speed. If we consider the earth and box as our system, what can we say about the net external force on the system? So which of these 5 statements is true? Well, 4 statements, and then 5 is saying it's none of the above. So read through them, think it through, talk it over with your physics friends, and then let's see what the answer is together. Okay, so the net external force on the system, it is zero, even though the system is not isolated. So an isolated system has no net force acting on it. It is not interacting with something outside of the system. This case, it is the net force on the system is zero, but the system is not isolated because there's this external agent that is acting on the system and is in fact doing work on the system, which is the next question. So because it's at constant speed, we have Newton's first law on equilibrium, but what is also true is that, well, so because of Newton's first law, the net force is zero, but not isolated because this person is acting on the system. And we'll see why that's important in the next question. So a person pulls a box along the ground at constant speed. If we consider the earth in the box as our system, the work done by the person on the system, is it zero or non-zero? So think about what you think the answer is, talk it over with your physics neighbor, and then let's go through it together. All right, the work done by the person on the system is non-zero. This is an important point, which is actually why I go through these 3 questions. So the displacement of the box is in the direction that the person is pulling. So the person is doing work on the box. The person is not doing work on the ground or the earth, because the displacement of the earth is essentially zero. So even though the person is not exerting a net force on the system of the earth plus the box, the person is doing work. If the box moves, it has a displacement. The earth does not move, has no displacement. So this is one of the catchy points, one of the difficulties in thinking about the work energy theorem. We're comfortable with the idea that forces between interacting objects are equal and opposite, from Newton's third law of motion, the work done by those forces need not be equal and opposite. And in this case, they're clearly not. The displacements are not equal in size, opposite in direction, or even in the same direction. There's no particular relationship a priori between displacements. So you have to be careful when we're thinking through work energy theorem and systems, and don't make sweeping statements that are just not valid. All right, last one. We have a stone and it's launched upward into the air. In addition to the force of gravity, the stone is subjected to a frictional force due to air resistance. The time the stone takes to reach the top of its flight path is larger, equal to, smaller than the time it takes to return from the top to its original position. So think about what you think the answer is, and then we'll go over it together. All right, the time it takes a stone to reach the top of its flight path is smaller than the time it takes to return to its initial position. This one usually bends people's noodles. So let's say, well, it's supposed to be a straight line for the ground. And then I have a trajectory of the stone. Something like that. A parabola, hopefully a better drawn parabola. The work done by air resistance, so frictional force, so that work is always negative. It's always slowing down the stone. So if I compare points that are at the same height, I'm always going to find, so it's going up on the left and down on the right, I can always pair those points up so that there's been more work done by the force of air resistance on the right-hand side than there is on the left-hand side. So the stone is always moving faster on the left-hand side in each of these pairs of points that are on opposite sides of the parabola, all the way up to the tippy toppest. So it's always moving faster on the left. It must take less time to reach the highest point than it takes to fall back down to the original height, which is not what you were expecting if you're thinking in terms of just projectile motion. Projectile motion, it's the same amount of time to go up to the highest point is to return to your starting height. With air resistance is always doing work to slow down an object, and therefore it is always going to fall slower than it rises.